and it's getting smaller and smaller and smaller and smaller. And as it gets smaller, that is the number of nanoseconds out of synchronization that the clock is. So all of a sudden, we went down from like 15 digits of clock being off to 4. That's 4 feet of wire. And right now, the clock isn't displaying the right time because inside all of us, there are 3 wolves. Inside each computer, there are 2 clocks. There's the PTP hardware clock, which is now really, really accurately synced, but there's the system clock, which tells your programs what time it is. In order to set the system clock, we have to discipline it. It wants to be told what to do. So this command in Linux disciplines the system clock through a very similar looking process with really big scary numbers to really small numbers, and it'll just pop in, and it's now displaying the same time across both. And it is now synchronized. So like, I've got all these numbers in this data, and like if I were on a show site, it'd be really great to have my clock kind of like change colors depending on how synchronized it is. So that's sort of what this bottom device demo is. But like, I really want to know as the engineer, like, how good am I really doing? Like, are these numbers actually believable? So I've got my oscilloscope here, and what I'm doing is the network hardware in these devices has a function called pulse per second output. And what you can do is you can program the chips in the network card to output a pulse every second, descriptive name, and you can measure that with a scope very, very, very accurately at the nanosecond level if you have a fancy enough scope. So what I'm going to do is I'm going to zoom in here. Right now we're looking at a 20 microsecond graph. So there's 20 microseconds on each grid line. But I'm going to go all the way down to a 100 nanosecond graph, and then kind of zoom in here past the limits of what my scope can do. So this line, each of these grid lines is 10 nanoseconds, 10 feet of the wire I gave you. And you can see that these 2 pulses coming from the 2 devices, that's what the blue line and the red line represent, are coming in within 10 nanoseconds on either side of one another. And this is basically showing me that I've synchronized these 2 circuit boards to within 10 nanoseconds. And of course, to demonstrate what happens when everything goes awry, what I'm going to do is I'm going to go to my network switch control page, make it smaller so we can see both at once, see if I can really get everything on one page. The new window snapping thing macOS added is going to be great. I'm actually going to like zoom back out a little bit because it makes it easier to see. But remember, we're like nanosecond level sync here. I'm going to turn PTP off on these ports, and I'm going to hit apply, which is off the screen because my window's there. And pretty much instantly, these numbers are going to shoot way back up, and my red line's going to disappear. And that's because I lost my sync timing. It's all the way over there. Come back. Sometimes it gets a little closer, but without any reference to the other clock, it's gone. It's never coming back. You'll also notice that the display on my clock has turned red because the numbers got too high and it's angry, and that's how I indicate the angriness of things. But what I'll do is I'll turn my PTP back on, and we'll watch it drift back into sync. So I'll hit apply. These numbers are going to start getting smaller. You're going to see the red line kind of home in on the blue line. At some point, the clock display will turn green, well, orange, then yellow, then green, as it goes through the various strata of being more aligned. If my software works, which it looks like it did, hooray. And we can zoom back in to that, 100 nanosecond maximum precision of my eBay portable, or my Amazon portable scope that I can take on airplanes. I didn't get a TSA love note this trip. So the last time I did this, I had those like metal computer cases with the Bowser sticker on it. They thought that was suspicious, but these went right through. So anyway, you can do all sorts of interesting measurements with this. Like if you have a facility where you're distributing PTP, you could use this as an ability to make sure that your network is properly distributing the time. And while there are $12,000, $20,000, $30,000 instruments that do this, I made this in my basement with a box of scraps for like this is kind of like the second or third polished version that we're eventually going to like turn into something we can use on shows. But like the first version of this is like you get a Raspberry Pi and you run some Linux software and like you can like inspect and mess around with PTP. So if you want to get into SMPTE 2110 and precision timing, I would recommend that as a way to start. There's a ton of interesting videos from like YouTubers who are like building their own clocks and cool stuff like that. There's a convention this week in San Francisco called Open Sauce, where there's like a bunch of people who go and they also, in addition to all sorts of other open source projects, they talk about their precision clocks they built at home, and I'm going out there to go visit that, so it'll be fun. And yeah, so back to presentation mode, if I remember how to use my computer. Does anyone have any questions? I think I've got time for one, because I've got like